Hello and welcome to the presentation of our work on the synchronization power of token smart contracts. I am Orestis Alpos from the University of Bern, and this is common work with Cachin, Giorgia Marson, and Luca Zanolini. First, let's consider the question, what is synchronization power and why should we care about it? As we know, a major issue with blockchains is scalability, and since consensus is in the center of blockchain systems, the question is how do we make it faster? And in this direction, we have seen a lot of promising results, such as sharding or parallel consensus instances. We have also seen layer 2 protocols which run on top of blockchain application. But we have also seen interesting work that tries to improve the efficiency of the consensus primitive itself and thus come up with a better primitive. However, what all these works have in common is that they do not consider the question for any two transactions. Do they need to be totally ordered at all? Or in other words, is consensus required for a blockchain or can one use a simpler primitive? In order to ask this question, first I would like to present a very short theory recap. Our work is on the so-called shared memory model. And here we have some concurrent objects which have a state and provide some operations. And for example, we can see here a consensus object. It has some internal state which is not shown here, and it provides a single operation called propose. This operation accepts a proposal, a proposed value, and returns the agreed value. On our model, there are also some processes which interact with the object by invoking the operations. And finally, an important notion is this of a consensus number. The consensus number shows how difficult a problem is because it tells you how many participants need to agree with each other in order to solve the given problem. So if you prove that a problem has a small consensus number, then you have shown that it is actually an easy problem because not many or none at all of the processes have to agree in order to solve this. And now coming back to our question, from previous results from Geraoui et al. In 2019, we know that the asset transfer or money transfer problem has consensus number 1. You can think of it as a blockchain similar to Bitcoin, where the participants transfer an amount of a currency among each other. And this indeed tells us that for a blockchain, we can use a simpler primitive and we don't have to sacrifice to use a lot of computational and communication effort as current blockchains are doing. And moreover, this paper shows that a K asset transfer problem has consensus number K. What this means is that if we have an application where up to K people share an account, then these K people have to agree in the total order of their transactions. And then the question that we ask ourselves is, what about smart contracts? Because modern blockchains go far from simple asset transfer applications. They offer smart contracts through which one can build any kind of application on top of a blockchain. So what happens there? Do we need to totally order all the calls to a smart contract? And to answer this question, we focus on a specific family of smart contracts, the ERC20 tokens. These are one of the most widely adopted smart contracts on the Ethereum blockchain. First, we model this as a concurrent object. It offers a number of operations. The most important for us are transfer from and approve. What these two approve allows the owner of an account to approve another second party a second process to spend up to max allowance tokens from this account. And now this second party becomes an enabled spender for this account. And the enabled spenders can then use the operation transfer from in order to transfer some tokens from an account for which they are enabled. And the question we have to answer now becomes, what is the consensus number of this token, of this object? Now, where things become interesting and challenging is when we observe that the approve function can be called dynamically at any point by account owners in order to increase or decrease the allowances of other parties. And moreover, when a party calls the transfer from method, then their allowance is also changed. And this dynamic behavior is what makes our object more complex than the previous results, than the k-asset transfer node that we have seen. But also it means that the consensus number now depends on the state of the object and changes with the state of the object. Thus, it's not possible to reason about it using standard techniques from the distributed computing theory. So how do we answer our question about the consensus number of our object? What we do is to define a partition of the state, a partitioning of the state into some state clusters which depend on how many processes are enabled for each account. And then our question becomes simpler. It says, what is the consensus number of this straight restricted object? And based on this, we can now prove our result. We show that this state restricted object has a consensus number k. And a detail which I will not explain here, but on our paper, we actually do it in two steps. First, we prove a lower bound by a reduction to k consensus and an upper bound through an impossibility proof. But to sum it up, what we have that this concurrent object for a well-defined set of states has the consensus number k, and we know that for each of those well-defined states, we only need to synchronize the calls of the enabled spenders. And with this, I would like to thank you, and I will be happy to answer any questions.